All right. Um, of course, I suppose I should look into your prescription if you need one. I remember when I was in graduate school, there was a guy who would sit in the back of the room and would always say, "Please focus your slides," even when they were perfectly focused. And despite he was immune to the suggestion that maybe his eyes needed adjustment. Very annoying. Okay, so, and isn't it wonderful now that we have these things, we no longer worry about focusing our slides for some reason. All right, well, we have, let's see, I'm sorry, administrivia. Nothing in particular. Let's see, I think, oh yes, I did post an adjustment, a couple of things we left out of the project spec, one of which you would have noticed, maybe if you had gotten to that point, and one of which you might have guessed, given the other things that we had in there as as extensions. But so just take a look at that. It has to do with the return types of functions and what was the other thing? There was how you specified. Well, it's left me at the moment. Anyway, there was something else in there as well. So that's all stated, and it has been added to the project spec. I'm glad to see that somebody is reading the lecture slides, since I just got a comment this morning that the lecture 12 slides hadn't been posted. Actually, the non-existent PowerPoint version of the lecture 12 slide had been posted, but of course that doesn't do any good. All right, so any other administrative matters to raise at this point, or other matters? I haven't been getting any queries. I haven't been getting any messages saying, please cover this in lecture, or please go over this in lecture. Again, let me invite you, before the lecture, of course, to send me anything like that, because it's valuable feedback for us to know what needs more coverage. And I have to say, on that note, let me also say that there's a lot of detailed material here. I've sort of suggested to the TAs that they focus you on the pieces of this that are important. I mean, this is one of these things where we throw a lot of stuff at you. There are certain points that are extremely important, and other points that are sort of nice to know, but they are of lesser importance. And for example, the details of exactly how we build the machines that you're seeing here, while I am teaching them and while we can test on them and so forth, they're not as important as understanding what the whole enterprise is about, and what and the basic way that these machines, once made, are supposed to be used. So I just put that out there so that you don't necessarily panic at the enormous volume of information that we push on you. Of course, I just said that I reserve the right to test on it, so maybe you do have to panic. Oh well, okay. So this is the example from last time, an example of parsing, and I asked what would happen how would we get into other parts of the tree? And here's an example of this one, where when we get down to, as I think somebody suggested last time, when we get down to, say, this one right here, where the machine that's running over E, let's see, where are we? E plus parenthesis E plus parenthesis, so E plus parenthesis, E plus parenthesis, E plus, and then parenthesis E, and then end parenthesis. We finally get to state 11 over here, and that tells us that at this point we can, our only option at that point is to reduce, and so there had better be a parenthesis or a plus afterwards. So this is the machine, and the interesting thing here is, in this particular case or in both of these cases, I have indicated right here where the red thing is, exactly what state you end up in. That will turn out to be of significance a bit later on. But these states are labeled, instead of being labeled final state or whatever, they're labeled with the actions that you should take, either reductions, or they also, if there are additional lines, edges leading out of the state, then possible shifts. And as long as I can build a machine like this with no ambiguities, then I've got myself a parser that will run in linear time, and, well, that's not immediately obvious that it will run in linear time, but it will, where actually time that depends on the size of the tree that you build and the size of the input. And we'll parse all of these things and uses up an amount of space that depends only on the depth of the tree that you build. Yeah. Do I always what? Well, that's an interesting question. So the only time the answer to that question would be no is if I have a case where there is a conflict. In other words, where there's a reduction. For example, if at this node right here, which says reduce e int to e if you see a right parenthesis or a plus, if there were also an edge leading out of here that said plus on it, we would have a problem. But in this grammar, we have no problems. Now, as for what you do when there are problems, well, that's the subject of another slide. So yes, in this particular case, you reduce when you can, as it turns out. Now, so if we can build ourselves a machine like this, life is easy. We can just do, just like we did with NFAs before, we just build a table, and this table has not just characters along the top, but terminal and non-terminal symbols along the top and states along the side. And each entry tells us is either something that tells us which state to go to next. So for every place we have, for example, this guy, for state 3, when we see a parenthesis, we'll have an entry that says go to state 4. And every time we have a reduction, it has things you can do, and therefore it doesn't, and therefore it's less important or you can get more compression of the table by taking advantage of that. But that's not a very interesting thing from a conceptual point of view. So here's what you get. Here's a section of the machine on the left, and there's the table that represents it. So we have states 3, 4, 5, 6, and 7 down the side here. For example, in state 3, if we see a left parenthesis, we're supposed to go to state 4, so I've represented that with an entry that says S4, shift into state 4. Likewise, if we are in state 5 and we see a parenthesis or a plus, we're supposed to take a reduction, so I've represented that with an R subscripted with the production that you're supposed to take. More often you would put a production number there, but I don't have a production number, so I'll just put the production itself. And all the blank entries are things that do not have transitions. That is, they would represent some kind of error. All right, so that is that. And it's a pretty straightforward concept at that point. Now, at this point, we go back and we're almost there. We've almost got the whole algorithm. The only thing we have to do is just a little bit of optimization. So I've been describing this machine as a recognizer, as starting from the left side of the stack of the sentential form and sweeping through it until we get to the current point in the input. And the problem with that is that it's obviously inefficient, because at any given time, the first part of the stack doesn't change. It's only the handle, only the top of the stack changes. So when you sweep the machine over that first part, you're going to get the same result you did last time. So let's just save those results and thus save ourselves a little bit of time. So instead of keeping the stack like this, instead of keeping this E plus E parenthesis E plus and so forth when we up to the bar, let's instead keep a complete list from the left to the red handle here. So if we look at this and look at the machine, you'll see that after seeing, starting at the beginning in state 0, after seeing E, you'll go to state 2. After seeing plus, you'll go to state 3, and so forth until we get to the end there. And we just save that. Every time we shift something new, we'll just put the new state that you would get into on the stack. And every time that we do a reduction, we just pop something, the result of pushing the non-terminal that you get onto the stack. So as a result, the time required at each step is to decide what to do next is constant. So there's constant time at each step. The amount of time required to do a reduction depends on the number of symbols you create, or alternatively on the size, number of symbols that you consume, or alternatively on the size of the tree, the number of edges in the tree that you create. And so the total amount of time is going to be proportional to the size of the input. So it's nice and efficient. So that leads to the following algorithm, just a piece of code here to say it all. Looking at the top of the table, so we look at the top state of the table. At each point, we look at the top state of the table, and we look at the next symbol of input. If it's a shift, then we push that symbol on the stack. We push the next. We push state K, the next state on the stack. And if it's a reduce, then we pop the appropriate number of symbols off the stack and push otherwise, if it's an accept, then we're done. We've recognized the string, and if it's an error, then we're done. And we have an error indication. Well, maybe we're done, or maybe we have to do something to fix things up. And that's it. That's the parsing algorithm. That's what it eventually boils down to. And the only thing that's left, of course, is this problem of how do we build the machine. Yes?
You do the reduction, and you push the resulting state back onto the stack. What state does
Okay, so here's our machine, and we had a specific state. So here we have E plus E plus E and so forth. We are in state, according to this, we should be in state number 5. So according to this, in state number 5, we have a production, we take reduction, E goes to int, which in the table looks like, and in the table that would look like right here, or here, I forget whether there's a parenthesis, I think there's a parenthesis after that. So we get this entry right here, which tells us to take this production. So this production has one symbol on the right-hand side. So that means that we pop one symbol off the stack, that's the 5. And that will take us back to state 9, which is right, oops, it isn't here. State 9 is this one right here. If we just now push immediately afterwards, takes us to there. So that's how it works. It's pretty simple. So one of the optimizations is that it turns out that this step where you go from where you do the reduction and you push on a new non-terminal, that step always succeeds. There's never an error there, and that actually allows you to compress those entries in the table a little more than you do the other ones. So that was what the efficiency thing is all about. But we're not going to worry about efficiency here. That's the job of this software that's doing all this optimization. Okay, so the next question then is, fine, so we've got this thing. Now, how exactly can we get some clue as to how we're going to build this machine? How does this relate to what we've done before? Now, although I don't think I make this points properly in the slides, the actual answer to this question is that what we're going to do is we're going to take Early's algorithm, the ideas from Early's algorithm, and we're going to extract something from them. We're going to extract a special case from them. So, and I'll explain as we go along. So let's suppose that we're in a situation like this, where we have e plus parenthesis int plus parenthesis int, and we have just passed that first parenthesis. So what that tells us is that, or what we know from this particular state, is that we're somewhere in the middle of doing e plus parenthesis e goes to e, somewhere in the middle of that. We've already seen the e plus parenthesis part, so we know that. We can tell that from what we've done so far. And that means that the rest of the input, assuming that we are right about this, let's say that that's just one possibility in general, and it turns out to be the only one in this case. In that case, then we expect to see an E, and that E is going to be created either by the E goes to int reduction or the E goes to E plus parenthesis E reduction, because that's what the grammar says. So we don't know any of that. We know that we must be to the left of one of those things, but we don't know which. And so what we do is we record this situation by simply recording all the possibilities at this point. And we do that using this, by now, I hope, somewhat familiar notation, which tells us that, I don't know what that ... is. So, which tells us that we are in the middle of, so we can represent this state of affairs by saying, okay, we're in the middle of a production that looks like this, and specifically we're right there. We've seen all of this stuff to the left. So to the left of us, we will find an E plus parenthesis. We know that. We're in a state where to the left of us, there has to be an E plus a parenthesis. At this point, we might be here or we might be here. Oh, and by the way, since we might end, it might also be the case that we are here, and the next symbol after us is going to be a plus. So these things over here will be the symbol that we expect to find when we finally get the dot to the end of this production. So we expect to find we could find an E with an E followed by an integer, and then the whole thing can be followed by a plus. How do we know that at this point, by the way? What tells us this must be the case? Yeah.
We still have more stuff to go, and it's not in the file, and we're looking at the first C in production.
Yeah.
And so we're going to have anything else other than a plus behind it.
Right. So we could, at this point, if assuming that we are in fact in this situation, then the next symbol that we expect to see after this E is a plus. Therefore, we will add it to the. Therefore, we will indicate that we expect to see a plus here. And also after this guy, and also if we get a, if in fact this E here is formed by this production, then the next thing we would expect to see is a well, it doesn't matter what production is. Afterwards, we expect to see a plus. So we add these two items here. So this information records what we expect to see after when we get to the records the possible situations we could be in based on the information we know. And each of these things looks like exactly like an item in Early's algorithm. In fact, if you go back and look at Early's algorithm, you'll find that all of these things, all of these items here, well, never mind, let's forget about the repetitions, but all of the first parts, these the things with the dots in them, you will find together in a column when you run Early's algorithm over this. The thing after the comma will be all the symbols that we see, all the symbols that we expect, the possible symbols that we expect to see when later in the string we finally get to the end of this production that we think we're in the middle of. So this says, I think that at the moment I am at the left of an E that's formed from a single int. And by the way, after I get past that int, I think that I'm going to see a plus. So I'm just keeping track of that information. So that's basically all the information that I have at this point. Now, how do I use this trailing information? Well, you use the trailing information in cases where the dot finally makes it to the end of the production, in which case that's how I know that that's how I'm able to say at that state, I'm supposed to take a reduction if the next symbol is one of these things. So, just to answer your question in more formally, and what we call an LR1 item is a pair that consists of a production with a dot in the middle of it, indicating how much of the production we think we've processed so far, and a bunch of symbols, or a terminal symbol that says what I expect to see when I finally get the dot to the right after beta, when I finally move the dot after beta. What do I expect to see after this? If you will, it's basically like follow. What do I think is going to follow X when I get to the end? So what I'm expecting to see at this point is something that starts with, or that can be derived from the combination beta followed by A. That's what I expect to see in the input. So that's an LR1 item, and you'll notice how this differs from the items in Early's parser. First of all, Early's parser didn't bother to do any look-ahead stuff. It doesn't need it. But Early's parser also keeps track of where alpha started. It keeps track of it's labeled S, I think, in our notes. Keeps track of the position in the input where alpha started. This one doesn't need to do that. And the reason it doesn't need to do that is that there will always be an unambiguous way to, because this is a deterministic grammar, there will always be an unambiguous way to reconstruct where this production had to start. And for that reason, you don't need to hold that information. But the other thing that's interesting about this is that if this is what an LR1 item is, that is a production with a dot in the middle and a possible following symbol, then there can only be a finite number of possible items. Unlike Early's algorithm, where you can have an infinite number because each one of them contained an integer, which was the position in the input. You can only have a finite number of these items. And therefore, the complete set of the possible sets of them are also finite. So we've got ourselves a nice finite machine. So basically, again, we throw away a lot of information. We keep track of what the next possible symbols are, and then we put all of this into a table. And basically, the table tells us what would Early do in this case. Right? What would Early do in this case? So here's an example of doing this for this grammar. And the steps that we do here, the steps in this process, look very much like the steps of running Early's algorithm. This is sort of like, there's a concept in computer science called we call it simulation. Abstract interpretation is the general term, in which you run an algorithm in general, symbolically, and see what the results are. So this is sort of like running Early's algorithm symbolically. And it says that we start, what do we start off with? Well, we start off with the start state. And we start out with the start state, and the production start goes to E followed by end of file. That tells us, oh, we must be to the left of an E symbol. Therefore, the only way we're going to get that is by using one of the E productions, like this one, of which there are two, this one and this one. And we can also see by the structure here that when we get to the end of that E, we're going to see an end of file. Okay, so we'll throw that into the mix. These two productions and we'll say that we expect to see an end of file when we get to the end. And having thrown these productions into the mix, we then see, oh, well, now we're at the left of an E. So we'll throw these two E productions in, and afterwards, after we pass that E, we'll expect to see a plus. So I'll just take advantage of the fact that I have, rather than list those all out separately, I have collapsed the two of them into one symbol here, so we'll enter these two productions with two possible look-ahead symbols, end of file and plus. All right, so now when we do that a few times and we see, okay, fine, we've got everything we're going to get this way. So next, let's look at the possibilities of what happens next. Well, at this point, we expect to be able to see either an int or an E. If we see it, let's take the simple one, int. We'll come up here, and now we do that thing that Early's algorithm did when it saw a terminal, namely it shifted the dot by 1. So we'll shift our dot, and we'll move this production over to here when we see int. We'll move the whole production, including the possible look-ahead symbols, and now we've got this thing, and this tells us, we should have a state in which, excuse me, a state in which we see an E followed by an int, an int followed by a plus or a end of file, and when that happens, we should reduce using this production. Likewise, when we see an E, we move the necessary items over here. This tells us that if at this point we see an end of file, we should accept. We're done. And if we see a plus, then we should carry on up to here, and so forth. So this is basically the construction, the LR1 construction. This is in effect what Bison does. Or something like this is what Bison does. It does a somewhat, well, actually, it can do one of several things, of which this is one now, I think. And it basically builds an abstracted version, a machine that's abstracted from all possible executions of Early's algorithm on this grammar, with all of the information about where the string starts squeezed out because you can reconstruct it. And that's it. That's basically what's going on behind the scenes. It's a little bit, it's daunting because all of these machines are big. They'll have hundreds or thousands of states or something like that, and you couldn't possibly construct them without help. But other than that, the concepts behind them are actually not all that tricky. Okay. So as I say, we have a machine that's good, but and the only reason that I'm presenting this to you, all of this detail, is I do want to give you some ideas. I never like tools to be completely mysterious. So it's always good to have some understanding of what's going on behind the scenes, because occasionally it turns out you have to use this information to interpret messages that you get. So let's see, we will go into that, we will start into that question. This is sort of the more practical side of this. What kind of errors am I going to see and what do I do about them? But first, I think it's probably time that we took a break. Questions? Creak, creak. Okay, good. I can always tell when it's time for the break because the noise level from all those chairs moving increases significantly. So why don't we pause here and start again in a couple of minutes. Yeah. I think there are directions. You submit it as Project 1.
As
by the team, from the team repository.
as Project 1?
Yeah. That's what I said. That's what the homework says, I think.
Okay.
Yeah.
Maybe I just didn't notice.
I think those are the directions, right.
Yeah, I'll read it more carefully.
All right. Why don't we get started again? Okay, so we can run into difficulties. I mean, if the grammar is not well formed, or it does not allow of determinism, we get into difficulties, one of which was alluded to before. We can be in a situation where, like this, we have a state, it has an item, it has these two items, and the second item should have a dot at the end of the gamma. So there should be the red dot should be right here. And in that case, that's telling us, well, if there's an A at this point, we can shift to the next state. That's what this is telling us. And this guy is telling us, well, if there's an A at this point, we can reduce by gamma. So we don't know, it's not telling us which one we should do. In fact, what it says in effect is that there are possible continuations of the string, starting with an A, that can make it valid either to take the first one or to take the second one. So obviously, for that reason, because there's the question, do we shift or do we reduce? This is called a shift-reduce conflict. And there are numerous causes. For example, if your grammar is ambiguous, you will often get this. This is one way it will manifest itself. So we talked about the if-then. I think we talked about if-then-else before. This is ambiguous. This grammar here for S is ambiguous because if you see if E, then if B, then S, else S, there's an ambiguity about, just S, else S, there's an ambiguity about which if the else is supposed to go with. And this manifests itself because at some point you're in this situation where you can either reduce if E then S, and the grammar also tells you, though, that this thing is possible, and therefore you don't know which of these two to do. And it will tell you that. Bison will report a shift-reduce. It will say there is a shift-reduce conflict in state foo, and it will produce this helpful little file that shows you what that means. Shows you that shows you basically these two items, and leaves it to you to figure out. That means that I've got some ambiguity in the if statement. Here's another typical ambiguous grammar that one might have if you aren't careful. One way that this occurs, and this sometimes occurs in hidden form, you'll do the classical treatment where E is formed from E plus term or E minus term. Term is formed from term times factor and so forth. And you'll make a mistake at some point going down that hierarchy and put an E or a higher level thing on one of the lower priority items or higher priority items, and that will give exactly this conflict in a disguised form. Okay, so in this particular case, the fact that we don't know whether E times E times E is supposed to group to the right or group to the left shows up as a conflict when we get to this point here. So first of all we're in this point at this stage right here. We have E times E. And we also have an item telling us that we could be at the beginning of an E plus E. In other words, that this E here could be an E plus E. And then after we have parsed an E, we will have this possibility. We'll either see E times E or E plus E star. And the problem is, if we see a star at this point, Oh, I never corrected this slide. Shame on me. This should be, I think the second one here should be a star. So if we ever see if we see a star, we don't know which one of these two to shift. Okay, so I think want to shift. Now I'm sorry, this slide has been crumped. I shall have to fix it. Imagine that this thing is star. We don't know which way to group. We don't know whether to reduce immediately or to continue shifting. Plus shows up in a somewhat different way. So we have in Bison, and I haven't updated this, but it also applies to Horn. We have a way of dealing with these particular shift-reduce conflicts. Now, not all shift-reduce conflicts are caused by these classical things like grammar symbols, but there are a few that are, and specifically those related to expressions. This often crops up, and so there's actually a way of dealing with this. You can tell the parser that I want you to resolve certain of these conflicts. So regardless of the fact that the algorithm is telling you that that this particular thing can go either way, yes, I know that, but I want you to choose one particular one over the other. And it turns out that that simple specification actually allows you to express grammars very conveniently, very concisely. So specifically what Bison does is it allows you to give precedences to operators. So from lowest to highest like this. And then it does a very simple thing. It takes every production that contains one of these termlets. Is there an example here? Yes, here we are. So here's an example of, yes, here we are. These are better formed. So here's an example where we have an expression pluses and times. And if we're in a situation where we see E plus E, we're immediately before that last E, then when we do this transition, we're going to get over into this state over here, where we can have an E plus E, and we can either reduce it, or we can shift the plus, or we can shift the star, depending on which one of those two it is. So what Bison did, they had a simple little heuristic. They say, okay, fine. Well, you just tell me the precedences, you just give me a priority for plus versus times, and I will use that to resolve this particular conflict over here. And here's what I'll do. I will take every these are left precedence things. So I'll take every production that contains just a single non-terminal that has a priority, like for example this one right here, E plus E. And I will assign to that production the priority of the operator that it contains, tweaked upwards slightly. So I'll assign it that priority, and I'll tweak it upwards. So I'll give plus a priority of 1, I'll give star a priority of 2, and I'll give this production here a priority of, say, 1.1. And then I will decide my shift-reduce conflicts by looking to see which has the higher priority, the symbol that I'm shifting or the symbol or the production that I'm reducing. So if my next symbol, for example, at this point, if my next symbol is star with priority 2, then since that production has a priority of 1.1, I will resolve this thing by shifting the star, which is the right thing to do. Right? Star has higher priority than plus. So you don't want to reduce this E plus E. You want to keep going. If, on the other hand, I see a plus, then the priority of this production over here is the same as that of plus, but tweaked up slightly. So that means I would favor reducing, and I would get an E plus E followed by a plus. And so obviously the same thing in reverse. If you tweak the priority of the rule downward a little bit, it becomes right associative. So this is a really neat trick, and it helps resolve shift-reduce conflicts. Now, practical note, The danger is that you will use it. Right? That's the danger. You will use it because Bison tells you or Horn tells you there's a shift-reduce conflict. You say, oh, I better put a precedence on something. Don't do that. And because usually your shift-reduce conflicts are the result of you doing something else wrong. So we will look into that next time when we finish up this subject.